Chapter 10 is all about how we actually use remote sensing and how these things sort of work, and so we're going to talk more about that. So you have some source of energy, or the incident energy like sunlight, comes down, hits the surface of the Earth. Some of it is reflected away. Some is absorbed in the atmosphere, some is absorbed by the object that it hits. So there's some degree of this energy balance that goes in different places. Remote sensing satellites have spectrophotometers that allow it to collect this information and measure what is being reflected. We also know what is being transmitted, and from the differences in that we can sort of piece together what is where. And here's the interesting thing. Just a little bit about light and wavelengths. Remember, the wavelength is the distance between the tops and the peaks, and the frequency is the number of peaks per unit of time or distance. Ultimately, we use this to characterize the particular energy we're looking at. And what we're really talking about is visible light. And so across the entire electromagnetic spectrum, which goes from all the way down to the tiniest of gamma rays to all the way up to the longest of radio waves, in between there's a very thin section between 0.4 and 0.7 micrometers that we can actually see, and that is called the visible range. And so if we looked at that, here's another way of looking at it in terms of how much of the energy is transmitted through the atmosphere. And you can see when you get to the really small frequency stuff, there's not much of it that's transmitted. It's mostly absorbed by ozone and oxygen and other things. And then as you approach the visible spectrum, that numbers we were looking at earlier, 0.4 to 0.7, you see that during this range, the yellow or the orange color goes much, much higher, and nearly all of the energy goes through the atmosphere without any difficulty. But then once you get above the red, you start seeing less of it being transmitted. And you also get a couple little peaks here, and these peaks are where water absorbs part of the infrared. And as you go on up through, there are other areas of transmission and absorption associated with different compounds, all the way through up into the microwave. So what this does is it creates this unique environment where different things absorb or reflect different frequencies of energy and different amounts. And so here we have a graph showing the wavelength across the bottom, and across the other axis we have the percent reflectance. So this is how much of the total energy that was put on a surface is reflected, and then across the bottom it's at each wavelength. So for example, then if we looked at the grasslands, which is the light green line, you see that it starts out relatively low in the blue end of the spectrum, and as we move more towards the red and the visible, it increases and drops back down. Then we get to 0.7, and then we get this huge spike, followed by a couple little dips as we move on out. Move from the grassland to the red sand pit, you can see that the color goes up much further as we approach 0.6, which is more towards red, which is what you would expect, and has a very different behavior moving on across. Piney woods would be very similar to grasslands, but they have a lower percent reflectance in the near infrared. That could be useful. Then we have silty water, which is basically just water that has a certain amount of sediment stirred up in the column, and you can see how it goes up to some point and then drops down and sort of carries on across the bottom, all having very different signatures. But you have to know where to look. For example, if you're trying to identify the red sand pits, around 0.6 would be the easy spot because it should be very bright. If you're trying to differentiate between grasslands and the piney woods, you want to get up in the near infrared, things above 0.7, because at that point the reflectance should be much higher in the grasslands than they are in the piney woods, and the water should be much lower than any of them. And so that's sort of where we're at with those. So here's what we're talking about. Light comes down, light bounces off, some is visible, some is not. And what they're looking at here in figure 10.6 is one of these ways we can sort of go about collecting this information, to think of other ways that we can label it, learn from it, categorize it, make some use of it. And so what we're talking about here is going to be something relatively simple called the NDVI, which is the Normalized Difference Vegetation Index. And what the NVDI does is it allows us to look at the amount of visible and infrared light and how those two change between one another. And by simply doing these equations where you look at how that works, where you take the near infrared minus the red divided by the near infrared plus the red, you get a percentage or a number, and that allows you to characterize the data very differently. And what really helps is it allows you to go from one image to the next where other things could have been causing problems, and so it may have depressed the overall amount of energy. It doesn't matter because we're looking at the ratio of one to another as opposed to the total volumes. So this is just some of the things that we can use. There are other types of stuff we could look at. These different bands we've talked about to some extent. We've talked about the transmission and absorption. I want to go back and just talk for a little bit quickly about what actually happens in the atmosphere before the light gets down to things like these trees. We have these windows where we have a high transmission, but in other places it doesn't work quite that way. And that's because we have scattering. We have things like Rayleigh scattering and Mie scattering and non-selective scattering. Rayleigh scattering has to do with these significantly smaller parts than the wavelength of the light, and it causes some interference. And then there's Mie scattering, and it's just when we hit particles that are roughly the same size as the diameter of the wavelength. And then we have non-selective, which is when we hit anything that's really bigger. And they all behave very differently, but it's important to kind of get an idea of what some of these things are. So look at your textbook. There's these wonderful little green boxes that give you things like atmospheric window and Rayleigh scattering. It tells you more about it. Read up on them. There'll probably be test questions. Okay, so we've talked about that, and we're talking now more about the spectral signature. Let's move on to the next. Alright, so the NVDI, I was already talking about that a bit, and if we look at it, what it does is it allows us to see healthy vegetation. If vegetation is healthy and green, it will look differently than if it's dying and brown. And that can come in really helpful. For example, if you look at a map of Africa and you look at the vegetation index, you can get some idea. The higher the number, the greener the vegetation, and the less green the vegetation, the more arid the region. And so you can literally see where the Sahara comes into play. The other thing we can look at is colors and what they actually mean. There's a couple of different ways we can look at colors, whether we look at a composite, additive or subtractive models. I'm not going to go into too much in that. I'm not going to spend a great amount of time going over that, but in general, with remote sensing data, we either have a single panchromatic image, or we have a multi-band raster where we have a band for each of the red, green, and blue colors that then go together to form the colors we need. Now, where does this data come from? Sometimes we get it from satellites. In satellites, you might have things like band 7, band 4, and band 2, and they're all in grayscale, and then from that you can pull out these different things and set up these different combinations. An example here in step 3, we're looking at 742, which is a unique band combination that is designed to allow you to see certain things. And there's multiple of these, but we can look at true color, false color, and standard false colors, and there's other things. You can look in your textbook to get some idea of the difference of these. Again, green boxes. True color is an image arranged by placing the red band in the red color, the green, and the blue in the blue. False color basically happens when we place the red, when the distribution of bands differ from placing the ones in their appropriate ones. And standard false color is when we place the near infrared in the red goes in the green goes in the blue, and the blue we just sort of forget about. And some more combinations. Here's what that kind of looks like when it plays out. If we look at an image and we put it in a false color infrared, what would look like A would look like B. Here we have 3 different maps, and This shows us something that's important. This looks at change over time, 87, 91, 2000, 2010, and you can see how the growth and development has occurred in the area as it's expanded. Okay, so as I'm finishing up here, I wanted to just add a little bit more. These slides I actually narrated, I think last year, but I wanted to add just a little bit more because every semester, every year, these classes move through at different paces, and we cover maybe slightly or just subtly different things. And I wanted to point out a couple things that maybe weren't as brought out in the narrations. When we talk about spectral signatures, what we're talking about is how we map the response across the various wavelengths in terms of reflectance and transmittance and whatnot for an individual item. Now that item could be a land use like forest, or it could actually be, you know, something like murky water or red sands. Whatever it is that we're looking at, we spectrally identify how it responds across the various wavelengths, forming those lines just like we had on that graph a few slides back. And that signature allows us to know what to look for and where, and we can actually then use that to look across larger images to find other locations that have a similar signature, other locations where we can find the same things that we're looking for in those other items. And so it's just a means of remotely identifying what we see on the surface. And that's basically how this works. So I wanted to point that out again just to make sure everyone knew exactly what we were talking about. And then lastly, I just want to emphasize that when you're taking this little quiz for this week, take the time to not just listen to the lecture, but to go back through and read the chapter and pay attention to all the little things like the little boxes that tell you stuff and whatnot. There's a lot of great information in there that will actually help you answer some of the questions. So take your time, read the chapter. That's chapter 10. Take the quiz. The quiz is on chapters 9 and 10. And then think about your answers. Go back, look through the slides, go back, look through the chapter, figure out exactly what the answers should be, what it means, and then, in your own words, answer the question. Alright, well, that's pretty much all I've got for you guys. So this is a relatively short lecture, but it'll go along with what you've got there as far as the assignment to do this week and the other readings. And I'll see you the week after Thanksgiving, and I'll have a nice review. We'll cover the last two chapters that we're going to lecture on, and I'll give you some study materials for the comprehensive final exam. So good luck, and I hope everyone has a wonderful Thanksgiving break. Bye-bye.